Hello everyone, this is Dr.P.Rathika, Professor, Department of Electronics and Communication Engineering, PSN College of Engineering and Technology. In today's class, I am going to teach you analog to digital converter. First we will see what is analog to digital converter. So analog to digital converter is an electronic circuit which converts analog signal into digital signal. That is, analog signal means it is a continuous signal, that is it varies continuously with respect to time. This analog to digital converter will convert this continuously varying signal into a discrete time signal, or it may called as digital signal. So in this graph we can see both analog and digital signal. The green color signal shows the analog signal. So we can see the analog signal is continuously varying with respect to time, and the red color signal shows the digital signal. So this digital signal is not continuously varying, but for a particular period of time the value remains constant, and this discrete signal is represented as digital code. So these two signals represents the analog as well as the digital signal, and all real world signals are analog signals. For example, audio signal is an analog signal which varies continuously with respect to time, and also this analog signal contains noise. But the digital signal is discrete in time, and also it is represented by binary digits, that is, it is represented by zeros and ones. Here the two signals are given separately. The first one is the analog signal. You can see it is continuously varying with respect to time. Also, this point is having the minimum analog value, and this is the maximum analog value, and we are having intermediate values also. So the magnitude is varying with respect to time. The other graph represents the digital signal. Here the magnitude varies with 1 and 0 alone. There is no intermediate value. So this graph shows the digital signal which contains only zeros and ones. Next we will see what is the conversion scheme used for analog to digital conversion. So this is the simple block diagram represents the analog to digital conversion. So this is the analog input. First, this analog input is given to the sample and hold circuit. So this sample and hold circuit convert this analog signal into discrete signal like this, or otherwise this process is called as quantization. Again, this discrete signal is converted into digital code, that is zeros and ones. So this is the basic conversion scheme we used for analog to digital conversion. Next we will see what is the importance of analog to digital conversion. See, we all know we are living in the digital world. So we need to store digital information. So all microcontrollers store the information in digital forms. Okay? So it is very important to convert the analog signal into digital form, and also we have to compress the signal before transmission. So for this we have to efficiently compress the signal. For this, the digital form is one of the best form to compress the signal. And for data transfer also, the digital form is more efficient compared to the analog form. And one more advantage is the digital data can be easily retrieved, that is, it can be easily reproducible. So for this reason, analog to digital conversion is very, very important. Next we will see different types of analog to digital converters. The analog to digital converter is mainly classified into two types. One is direct type analog to digital converters and integrating type analog to digital converter. The direct type analog to digital converter compare the given analog signal with the internally generated equivalent signal. So this is the technique used in direct type analog to digital converter, and the next type will be the integrating type of analog to digital converter. Here the conversion takes place in indirect manner, that is, first the analog signal input signal is converted into a linear function of time or frequency. Again it is converted into digital form. And in integrating type there are two main sub-classifications. Classification is there. One is charge balancing analog to digital converter and dual slope analog to digital converter. Similarly, in direct type analog to digital converter, there are four sub-classifications are there. They are parallel comparator, or it may be called as flash type analog to digital converter. Next one is counter type analog to digital converter, servo tracking analog to digital converter, and successive approximation type analog to digital converter. So in this presentation I am going to explain about the direct type of analog to digital converter. I am going to explain first the parallel comparator type or flash type analog to digital converter. So the parallel type analog to digital converter is the simplest method to understand, and the circuit diagram is shown in the figure. So here the flash type analog to digital converter consists of the following components. Here it consists of a series of resistive network, and it have 8 comparator. So this is a 3-bit analog to digital converter. So it consists of 8 comparators, and it also have a 8x3 priority encoder. So here we are having a series of resistive network which have 8 resistor. All the resistor values are same, and the voltage across the resistors are divided equally. So this is the reference. At this point we have given the reference voltage, and this point is grounded. So if you measure the voltage across this point and this point, we will be having the total voltage of VR. This VR is equally divided across the resistive network. See, for example, suppose at this point if you measure the voltage will be 0 volt, and at this point if you measure, the voltage will be 1/8 of VR. Similarly, this point 2/8 of VR, that is equal to 1/4 VR. At this point we will have 3/8 VR, here 4/8, so it is 1/2 VR. For example, suppose if you are having an input reference voltage of 10 volt, at this point if you measure, you will have 5 volt, that is half of VR. Similarly, at this point 5/8 VR, and here 6/8 VR, and 7/8. If you measure this point, 8/8 VR, that is the total reference voltage we will have. And this op-amp operate as a comparator. The comparator output is taken as x0, x1, x2 up to x7. And this is the encoder. This convert the 8 input to 3-bit output. The output is taken as y0, y1 and y2. This y2 represent the MSB and y0 represent the LSB. MSB is nothing but most significant bit and LSB represent the least significant bit. So before going for the operation of this circuit, I will explain the comparator logic. So this truth table represents the comparator logic. In this circuit we have used 8 comparator. Each comparator is having 2 input. At positive input we have given the analog input voltage. Here you can see all the positive terminal of the op-amp is connected to the input analog signal. So this is all the positive terminal is connected to the input analog signal and the negative terminal is connected with the resistive network with different level of voltage. So whenever the analog voltage is greater than that of the voltage applied at the negative terminal, the output will be 1. Suppose if the analog voltage is less than that of the other end voltage, the output we will get is 0. Suppose if both the terminal are having the same voltage, then the previous value will be given as the output. So this is the truth table followed for comparator. So suppose if the output voltage is greater than 1/8 VR, so assume that if the output voltage is greater than 1/8 VR, so this positive terminal is having the highest value compared to that of the negative terminal. So x1 is set as 1, also x0 also set as 1. So the remaining x2, x3, x4, x5 and x3, x6 and x7 are set as 0. Only x0, x0 and x1 will be set as 1. So the output of the comparator represents 1, 1, 0, 0, 0, 0, 0. So again this 8 output of the comparator is converted into 3 digital output by using this 8x3 priority encoder. The truth table for this 8x3 converter is shown in the tabular column. Here you can see here, if the input voltage lies between 0 to V reference divided by 8, then only the x0 bit is set as 1. That is, the output of this comparator alone will be set as 1. Other remains 0. That is represented in the truth table. So other outputs are 0 except x0. So the output will be 0, 0, 0, 0, 0, 0, 0, 1. By using the encoder, this 8-bit is converted into the 3-bit digital output. So if the output of the comparator is like this, then the 3-bit digital output will be 0, 0, 0. Similarly, if the input voltage lies between V reference divided by 8 to V reference divided by 4, then both, as I have explained earlier, both x0 and x1 gives the output as 1 and the remaining digits are 0. In this case, the encoder will give the output as 0, 0, 1. Similarly, if the input voltage lies between VR divided by 4 to 3 VR divided by 8, then in addition to X0 and X1, X2 also set as 1. So in this case, the output will be, 3-bit output will be 0, 1, 0. Similarly, if the input analog voltage lies between 3 times of VR divided by 8 to VR divided by 2, then X3 also set as 1. So in this case, the output code will be 0, 1, 1. So this repeats up to the maximum voltage of VR. So this is the 3-bit representation. So the final value or the maximum 3-bit value will be 111, which is the output for the output for the input voltage, which lies between VR divided by 8 to VR. So this is the maximum output we get. So this is the 8 zone. So this will divide the analog input voltage into 8 zone. So for each range, the output will be one code. That is, if the input voltage lies between 0 to VR by 8, until VR by 8 we will get only 0, 0, 0. If you want to increase the precision, then we have to increase the number of bit. That is, we can go for 4-bit or 8-bit conversion. Next, we will see the advantages and disadvantages of this parallel comparator type analog to digital converter. So it has high speed of conversion because it converts the analog to digital signal simultaneously rather than sequentially. Also, the conversion time taken is 100 nanosecond or less. So within 100 nanosecond, it can convert the analog signal to corresponding digital signal. And the only disadvantage of using this flash type is the number of comparator required is almost double that of each added bit. See, for example, here we have used 3-bit converter. For this we needed 8 comparator. Suppose if you go for 4-bit conversion, we have to use 16 comparator. So that is the main disadvantage of this flash type analog to digital converter. Next, we are going to see the next type, that is successive approximation type analog to digital converter. So this is a very efficient conversion method, and it can convert the n-bit conversion just in n clock periods. So for example, if you are going for an 8-bit converter, it requires 8 clock pulses to obtain a digital output. This is the functional block diagram of successive approximation type. So the circuit is having a comparator here, and here SOR, which is nothing but successive approximation register. Also it having a digital to analog converter, and a clock pulse is given as an input to this SOR. Also it is having two signal, that is SOC and EOC. SO is nothing but start of conversion and EOC is nothing but end of conversion. Also this picture represents the functional block diagram of 4-bit converter. So here in this output we are having 4 digital codes, start from D1, D2, D3 and D4. D1 is nothing but the MSB. MSB means most significant bit. So D4 is the least significant bit. So in this analog to digital converter, we are using a digital to analog converter, which convert the output of digital signal into corresponding analog signal, which can be compared with this comparator. So here VA is nothing but the analog input which we have to convert into digital. We will see the operation of this circuit. So here we are going to give the analog signal as input and it is connected to the positive terminal of the comparator, and in the negative terminal the output of digital to analog converter is given. So the output of the comparator is given to the successive approximation register. We can explain the operation by using the truth table. See, initially whenever the circuit receives the start of conversion, at this point the MSB bit is set as 1. See, in this truth table it shows the conversion for 8-bit converter. So here, see, for example, suppose I have to get the output like this, that is, for the given analog input, the output of the digital converter should be 11010100. So now I am going to explain how we are going to get this output. So whenever we receive the start of conversion signal, the MSB bit is set as 1. The remaining all bit set as 0. So now the output of the 8-bit converter will be 10000000. Now here you will get the 8-bit digital output. Now this digital to analog converter will convert this 8-bit digital output to corresponding analog signal. So that is given as the input for the comparator. So at one terminal we are having the input analog signal, and the another terminal we are having the output from the digital to analog converter. Now we have to compare this input analog signal with the DAC output. That is, the DAC will give the analog signal corresponding to this digital code. Now if VA is greater than that of this VD, then the output of the comparator will be 1. When the comparator output will be 1, then the next bit will be set as 1. Now this digital output will be converted to corresponding analog output by the digital to analog converter. Again, now the comparator will set the analog input analog signal with the VD. VD is nothing but the output got from the DAC. Again it will check. Suppose if VA is greater than that of the VD, the output will be 1, or otherwise the output will be 0. Suppose if the comparator output is 0, in this case, now this voltage, that is this digital code is greater than that of the digital code. So the output of the comparator will be 1. So next what we can do is, next this bit, third bit also set as 1. Now the digital to analog converter will produce the analog output corresponding to this digital code. Now this analog value will be compared with the input analog signal. While comparing, we will get the negative result because the analog input is less than that of the analog output of this code. So next what will happen means, the third bit, last, which bit as set as 1 remains 0, and the next bit will be set as 1. So you can see here. So in this step, the third bit also set as 1, but in the next step, this bit is set as 0 and the next bit is converted to 1. Now this digital to analog converter produce the analog signal corresponding to this code. Again this will be compared with the analog signal. Now this given analog signal is greater than that of this one. So in the next step, the next bit is set as 1. Again the process is repeated. So next this code is converted to the corresponding analog signal. This analog signal is compared with the analog input.